We're going to go over a little bit of the projects that we're planning to do for LNet, and maybe if we have time, cover a little bit of the development that happened last year. So the outline is just we're going to go over the projects, like I said, and then there was a few problems with non-contiguous buffers that creeped up, and we did some rework that is a little bit user visible, so we're going to maybe cover that as well. So over in 2.10, we landed Multirail. That's been used a little bit in a few sites. Also, this in 2.11, we landed LNet Multirail Dynamic Discovery. So the dynamic discovery makes configuration easier, so we don't have to configure every peer on like every peer on every other peer to tell it that the other peers are Multirail, every interface of the other peer. So in that was landed in 2.11, and it's passed our testing, so hopefully people are going to start using it. Then there are two other parts that are related to the Multirail projects that are going to hopefully land in 2.12 and then 2.13 later on. So I'll cover the first one, which is LNet Health. So now that we have multiple interfaces, we can aggregate their performance, but it's always good to make sure that we are resilient. In case one interface fails, we can transfer to another interface. So this is LNet Health or LNet Resiliency. And the idea is to be able to retransmit the messages on different interfaces of the remote. So if we detect that the remote interface has failed, then we switch to using another remote interface. And if we find that there's a local interface failure, then we switch to using a different local interface if we have that. We're going to add some capabilities of detecting failures down at the LND. So that's the driver of the driver that deals with Mellanox or OmniPath. We're going to add some capability to detect failures there and report it up to LNet so that LNet can deal with it. Also, right now, so RPCs are composed of multiple puts and gets, and puts usually require an ACK, and gets always require a reply. But the caller that sends the put or the get are required to set their own timeouts. So we're going to implement a common timeout mechanism for the ACK and reply to make sure that if the ACK or reply are not received within a specific time, we can time out this put or get and let the upper layers deal with it. We have some documentation already. The scope and requirement document is in that link, and then the high-level design is also there. So if anybody is interested, they can go read this and put in their comments. Or if they think something else should be added, they can do that as well. The implementation is going to happen on the Multirail branch. We already have a bunch of patches, but they haven't pushed up there, but they will be pushed up fairly soon. The next thing that we're working on right now also for 2.12 is LNet SysFS. So currently LNet Control, which is the utility used to read LNet statistics or configure the system dynamically, etc. This all happens over IO control, and we've been doing a push to move all the statistics to the SysFS interface. So we're moving this project will make sure that we expose all the LNet AutoIBLND and SOC LND statistics all to the SysFS file system, and then be able to read it from the SysFS and present it in YAML format to the user. Right now, there are some statistics, but they're not comprehensive, and we're looking to add more statistics on connections, LND peers, etc. That are currently not visible, and being able to show that up to the user, it will make debugging easier. If there is a problem, we can dump the stats and we can have a better view of the system. Again, documentation is there. We have the scope, HLD, and test plan if anybody's interested in going and taking a look. That's the fourth and final part of the Multirail project, which is the user-defined policies. So there is a desire to be able to fine-tune the selection algorithm. So the way Multirail works is when you have multiple interfaces that you can send over, you start selecting the interface based on its NUMA closeness to the memory of the buffer that you're trying to RDMA. Or then if that's close, then you look at the credits, and if that's equal, then you do you do just round robin. But it's important sometimes to define policies to say I always want to prefer like auto-IBLND, for example, and keep TCP only a TCP interface only for a backup. So we want to be able to define policies at the user level in order to guide the selection algorithm to make better or more intelligent decisions. So there are 4 rules that we're going to look at. There is the priority, LNet network priority. So you set a priority on the network. And then when the selection algorithm goes through it, it will obviously prefer the networks that are higher priority. Say, for example, again, you have a TCP network and you have an auto-IBLND network. You can set auto-IBLND network as a higher priority, and then it will always select that unless it is unavailable or goes down, then you select the TCP one. Another rule is the local NID rule. So if you prefer, for example, a specific local interface that you want to go out of and keep the other interfaces for backup, you can do that. Remote NID rules, the same thing. And peer-to-peer rules is kind of combination of the local NIDs and the remote NID rules. There's also a potential of, for example, using the same algorithm to select routers. Like if you want to subdivide the routes and make sure that you select routes based on a specific policy, this kind of general algorithm can be applied for that as well. Another project which it's been kind of in development, it's not anywhere right now, like it's not anywhere public right now, is the unit test framework. So we have no functional way to test LNet and all the different features that we're implementing. So we developed this unit test framework based on Python. So you write all your scripts in Python, and then it interfaces with LNet config to configure the system in whatever way you want. And then you can interface with LNet self-test. So for example, you can configure a net, and then after that, go and run some tests. Then while you're running some traffic, then you go and delete a network. And then after that, you can run some extra traffic to make sure that deleting the network worked, or changing the routes. For example, if you have multiple routers, you can set up 2 routes, run traffic using LNet self-test, bring one of the routes while the traffic is going, and monitor your statistics to make sure you're switching to a different route. So this is what we're trying to achieve with the LNet unit test framework. Other things we've been doing is some documentation. Like you saw, we're trying to have a scope and requirements and HLD document for all the projects we're doing. But also more than that, some of the code that's in LNet has no detailed design, and sometimes it's hard for new developers to go and take a look and understand this stuff quickly. So we're trying to write more detailed design in our wiki link down here, so that people can, if somebody's looking at some code and want to look at the documentation, they can take a look at some of the descriptions that we wrote here. That's kind of incremental. Whenever we run into something like connection management or MapOnDemand or whatever, we document it to make sure that when we go back, we don't forget, we don't have to reread the code again, right? Another thing, and now we're getting to the point where there's a bunch of features that are a little bit farther ahead. Hence, there is no release number associated with it. So there's a bunch of auto-IBLND RDMA changes that we need to do. One of them is there's a new fast reg memory API that Mellanox has put out there. This is, like, I'm not gonna go into the detail of that, but it's documented in that PDF. So we need to switch. We're currently using the old API. We need to switch to the new API. There is a new CQ polling API completion queue polling API. That there's actually a patch that's already landed. Doug did it, Doug Ocherek, and it's currently under test and review. The point of that, the CQ, it will simplify the queuing mechanism or the queuing algorithm that we do, or the completion queuing polling algorithm that we do right now. Then there's another one which I think is fairly important, draining the QP. Right now, when you create a connection between two peers and you try to close that connection, if there are any outstanding work requests on that connection, we have to wait for all the work requests to complete before we can close the QP. And there is a problem that there is no time limit on that wait. So we could be waiting indefinitely, and we need, so there's a new API that Mellanox added to drain the QPs, which forces the QPs to close, and then this way we don't have to wait indefinitely. So these are the new API changes. There's also one that is not documented here, but that's coming down the road. Mellanox might add support for non-contiguous buffers. So they put up a presentation in the Open Fabrics conference. So that's another thing we need to look at in more details. Few requests that we've been getting is how do we test our routing? Like routers, how do we test them? So we did write like a test plan for our LNet routers, and we need to translate that test plan into an actual set of unit test framework test scripts. Yeah, so that's something that we have the plan, but we need to implement the actual test scripts and have them automated. Another thing that James kind of touched on, again, that's in the future a little bit, is we want to improve LNet self-tests. Right now, the user interface is not great, so we're thinking about using YAML to interface with LNet self-test. And we also want, like right now, LNet self-test doesn't reflect the call flow that Lustre does. So we want to be able to specify a specific call flow in using YAML and get self-test to actually run that in a bursty fashion. Again, we want better integration with the UTF so that when we can interface with it a little bit better. So like I said, we can do some configuration, run some traffic, change the configuration while traffic running, look at the traffic results, and so on. There's another one, again, it's a little bit in the future. There is, Cray entered this ticket. It's about expanding route failure detection. Right now, if a route fails, we only detect it if it's literally the next hop. But if there is a chain of routers and then one of them fails down that chain, we won't know about it like with the current mechanisms. So the proposal on that ticket is to be able to add an extra feature in the, extra field in the ping as with the route status up and down, so that when you route, if as you go along the ping, if it pings the next router and the router is down, then it can send a response back with the state of that route. However, that kind of it's not backwards compatible. So there is another protocol that's out there we have an implementation of it called the Gossip protocol, and it's supposed to be able to discover the network around it in an efficient way. So we're looking into, we want to look into how we can integrate it in Lustre and use it. Again, one other project is the IPv6 support. We want to expand the NIDs to support IPv6 addresses. Obviously, that will break the LNet compatibility. So, like for example, on one that uses IPv6 can't talk with an IPv4 because the NID sizes are different. It changes the wire protocol. So what we want to do is we want to be able to, maybe one way to resolve that is to add routers in the middle that handle routing between IPv4 networks and IPv6 networks. Do I find, okay. So for the recent developments that we've been doing, like we said, we had, there was a patch that was landed in a while ago. The result of that patch was it sent a non-contiguous buffer to LNet. And LNet assumes that all the buffers it receives that to RDMA over are all contiguous. It could have an offset at the beginning of the buffer, and it could end at a non-page aligned ending, but in the middle it should all be contiguous. With that patch, we started seeing a problem, but it only manifested itself in RHEL 7.4. And the reason for that is in 7.3 and earlier, we used global memory regions. And that, how we dealt with that is we actually described each fragment, like the start, offset, and the length of it. So we never saw that problem. But once we switched to 7.4, where global memory regions were taken out because of some security concerns, and only FMR and FR, fast regiment, FMR and fast, it's kind of confusing, FMR and FRMR. FMR is for Mellanox 4, and FRMR is only for Mellanox 5. So anyway, when those were used, what we do is we describe all the buffers as just one big fragment, and we transfer it over. But when there's fragments or gaps in the middle of the buffer, the algorithm that FRMR and FMR uses, they don't work, and they cause corruptions. So we needed to deal, this is kind of an example of that. We have a scatter-gather list with maybe an offset at the first page, but the third page has a gap right there, and then it continues. So if we try to RDMA that normally, then we end up with a memory corrupted data transferred over. So I described the problem. So that led to a set of patches that we landed to deal with this. The first patch was to simply just, fix the luster to ensure that it always sends aligned pages. So that was one way to hide the problem, but this problem still existed in the LND driver, so we needed to fix it at the LND driver. So the final solution that we ended up doing is we wanted to get rid of MapOnDemand because it's kind of confusing. MapOnDemand is used when you set it. What it does is it checks if MapOnDemand is set to something, then we try to, say, okay, I'm going to give an actual example. So say we set MapOnDemand to 32. That what we're saying is if the message that you're trying to RDMA over can fit within the 32 fragments, then use global memory regions. But if the RDMA that you're trying to transfer over is larger than 32 fragments, then we should switch to using FMR or FRMR. By doing that, but moving forward, we said that the global memory regions are simply going to be, they are removed from the kernel. So there is no need really for MapOnDemand anymore. So we decided to set it to make it non-configurable. So it's always set to 256. And then we try to transmit, but because there is, to handle any backwards compatibility, we have to look at the other peer, and if the other peer has it set to lower than 256, then we still have the negotiation protocol going on to negotiate a lower value. Other than that, we're just going to use 256 and transmit the buffers that way. But there was a fallout with that. First, because we are using 256, which is the largest number of fragments, sometimes the QP, when you create the connection, it fails because there isn't enough memory. And that we've seen that in some bugs, and also in the OPA when you're using omnipath TID RDMA, because TID RDMA allocates everything using statically. When you allocate such large amount of memory, it can fail. It can actually crash the system with out of memory. So we have a ticket currently open to see how we can reduce the 256 to something reasonable, because really with FRMR or FMR, you only need 3 work requests, so you can actually only reduce that 256 to only 3. But we need to figure out a way to do it properly. And that we're looking to do that, hopefully landed on master soon. And the MapOnDemand rework that I described is in 2.11. So just to conclude quickly, we have LNet Health is landing. LNet Health and SysFS are landing in 2.12. user-defined policies in 2.13. The unit test framework is ongoing, and hopefully it will be out there for people to use and integrated in our normal test system soon. And then I just covered the auto-ability non-contiguous buffer support quickly. Okay. Any questions?
So in your multi-rail user-defined policies, I'm thinking of Bob Shehata's question earlier about as we get to data and metadata, and maybe you want to separate the data transfer traffic from the actual metadata traffic. Is there some possibility that we could have MDS with two different LNet policies, one to drive us through two different interfaces?
The problem with that is LNet has no concept of metadata or servers or whatever. It just sees peers, so we won't be able to really know whether this particular traffic.
Yeah, no, I mean, this would be something you hadn't thought of yet, but maybe there'd be some way to drive down what the content is, what the purpose of the transfer is to let you make that decision.
I have to think about that. Right now, it doesn't do anything like that. What I was thinking, though, about this is you can actually set quality of service policies to drive specific cluster traffic over different VLANs or whatever, right? So there is a way to do it, but I'm not sure. Right now, the QoS service is actually like on all of Lustre traffic, not on only specific. So I don't know how we can separate the different types of Lustre traffic.
I'm just thinking that with the single connection per client to MDS, that there's really no, I mean, we're trying to separate that traffic, not traffic to other things, right? We want some of that traffic to go on a high performance path, some of it to go on a low performance path.
Are you saying we have two interfaces, we're going to use one for only specific type of traffic? And
right, it might be a virtual interface or it might be a real interface, but yes.
You can add a policy to say, if you're talking to that interface, always use a local interface, so you can separate it that way. But you'll have to know beforehand which local interface you're going to use. Like, no, I have to think about that.
Yeah, no, I'd be happy to talk to you about it if you want.